In this video, we're going to talk about statements that have two quantifiers. This is very important because this type of statements is going to appear over and over again in analysis. For example, in the definition of convergent sequence, in the definition of limit of a function, definition of continuous functions, and many more. So it is extremely important that we become very comfortable working with the statements with two quantifiers from the beginning. And we're going to see that the order in which the quantifiers appear matters a lot. So before we start with a math example, I want us to take a look at a more everyday example. Take a look at this. If I have H is the set of all humans, I want you to translate into English the following statement. For every X in H, there exists a Y in H such that Y is the mother of X, and there exists a Y in H such that for every X in H, Y is the mother of X. If you look at it carefully, these two statements are the same, just that the quantifiers are swapped. So, when I'm saying translate into English, I mean translate it into plain everyday English, just like the language you would use to talk to your friends or to talk to your grandma. I do not want you to write a robot translation. So something like, for every human X, there exists a human Y such that Y is the mother of X. That is not allowed. You have to write it, as I said, in everyday plain English. I invite you to pause the video and write a translation of these two sentences. And it is very important that you pause the video, because if you do not think about this question carefully before you see the solution, you're going to rob yourself of the opportunity to learn and understand very well the meaning of these quantifiers. Okay, welcome back. I hope that you have your two sentences ready, and now let's take a look at my translation and compare it to yours. There is more than one correct way of writing the translation, and it's often the case when we translate from one language to another, but the important thing is that the meaning is the same. So let's take a look at this. Here, when we say that for any human X there exists a human Y such as Y is the mother of X, we're just saying that every human has a mother, at least a biological mother. And the other one says, well, there exists a human, there is the mother of every human in the world. And well, that would be lots and lots of children, and we know that's absolutely not true. It's impossible that there is one woman that is the mother of every single person in the planet, including herself. So this tells us that indeed swapping the order of the quantifiers makes a huge difference. So be careful when you're writing a definition in mathematics. Think carefully what you mean, because the order matters. Let's now take a look at a math example. Here we have two statements. The first statement says that for every real number X, there exists a number Y such that X is bigger than Y. And the second statement says that there exists a real number Y such that for any number X, X is bigger than Y. Now, if we take a look at them, we can notice that they're the same except for the fact that the two quantifiers have been swapped. And we need to explore exactly what they say and see what the differences are. The first statement is telling me the following. It says, first choose any real number X. So here I have my hat, has all the real numbers in the world. Trust me, here I can fit all the real numbers. And what I'm going to do is I'm going to give it a good shake. I'm going to close my eyes. I'm going to pick randomly some number. Okay, see here we have number 3. Right? So you have number 3 here. And for this number, I need to find a number Y that is smaller than 3. Okay, and now I'm allowed to look because I have to choose one based on my choice of X. So I have my X, was given to me, I couldn't pick it. But now the Y I can pick, I'm going to look. And indeed here I found -1 is a good candidate for my Y, because -1 is less than 3. And now let's say that I give another shake, very good shake. Okay, I'm going to pick a number. Okay, so now I have number 5. And again, for this choice, for this number 5, I need to find a y that is less than 5. So, okay, I'm going to go and pick here. Okay, great. Pi is less than 5. So this also works. And you see, pi wouldn't have worked before with 3. Pi is not less than 3. But this is not a problem, because now in this case, someone gives to me an x at random, so I pick my number without looking, and then I can search for one that is smaller than that number that I had. So then what is the statement saying really? Well, it's telling me that for any number that is given to me, any real number x given to me, I can find another real number that is smaller than it. Or in other words, that every real number is larger than some other real number. And now let's compare this to the next statement. So the next statement says there exists a y in R such that for any x, x is bigger than y. So here we're going to start with a fixed number. For example, let's say y. So my y is 0. And now I have to, well, close my eyes, give it a good shake because it has to work for any x. I'm going to do that. Okay. And let's see what we get. Just give it a good shake. Okay, we got minus 1000. Negative 1000 is definitely less than 0, right? So that means that this x that I got doesn't work, because remember, I had to, for this number 0, I needed that any number that I picked from my hat was bigger. This doesn't work. So that means that my y cannot be 0. Okay. Let me see. What happens if I start with y equals negative 1000, let's say. So just to start with what we left. Okay, so if I do this and I give it a good shake to my hat and I pick something at random, see, good shake, we got number 4. 4 is indeed, that 4 is indeed bigger than negative 1000, but that doesn't mean that we're okay. Well, not really, because what if I give it another good shake, close my eyes and pick one at random? Oh, we got negative 10 to the power of 9. That is less than that. So my x, which is negative 10 to the power of 9, is less than my y. So that is not good for me. Okay, but now, is it possible to find a number that is super negative, such that is the smallest real number? So can I find number y that is smaller than any real number? Well, let's see. What happens if I start with just y, the number y? So if I just do this, well, if I shake many times, eventually I could end up with something that looked like this. So it's y minus 1. Y minus 1 is less than y. So no matter which real number y I pick, I can always define x to be y minus 1. And then x would be smaller than y. So this is never ever satisfied, because no matter which real number y we pick, y minus 1 is less than y minus 1000 is less than y. So this is not true. Okay, so let's go back. What this statement is saying, that I fix the value of y before I look at any of the values of x. And then for that y that I chose, x has to be bigger than y no matter what x we chose. And we saw indeed with the hat experiment that this was not possible. And if we want to translate it into plain words to make it more sense, that what this means is that there is a real number that is smaller than all real numbers, and we know that is impossible. Perfect. So how can we prove statements with double quantifiers? We saw that the first statement was true, so we have a chance of proving it. So we want to prove that for every real number x, there exists a real number y such that x is bigger than y. Okay, so what is the first thing that we need to do? Well, we need to prove that something is true for any real number x. So I don't get to pick the x. Remember, I had to have my hat, shake it, and pick one without looking. The only thing that I was allowed to assume about my number x was that it was in the hat. So the only thing that I was allowed to assume is that x was a real number. So that's what we're going to do. We're going to start by fixing an arbitrary real number. So what we mean when we say arbitrary is that I don't get to choose which one. It could be any. And by fixing is that now for the rest of the proof, x has a value. So when we have a quantifier like for all is not fixed, so it's not possible to manipulate it and define new things based on it. But now x is fixed. For the rest of the proof, x is a fixed real number. And based on this x, remember, so for example, if I want to find a number smaller than x, can you think of a number that is less than arbitrary x? Well, one option is to pick y equals to x minus 1. But I could have picked y equals x minus 2, minus pi, or x minus 1,000,000. Doesn't matter. As long as my y is less than x, we're good. And this step is very important. So we want to show that for every x there exists a y. And remember, we said that to prove something about there exists an object, it is enough to give an example. So here we're giving an example of what kind of y's we allow. So we choose a y. But we're not done. We chose a y, but now we have to show that indeed my choice of y works. And to do that, well, we just need to check that x minus 1 is a real number, and we need to show that x minus 1 is less than x. But in this case, that's simple, right? Because x is a real number, x minus 1 has to be a real number, and, well, x minus 1 is definitely less than x, so that's it. So in general, this is the structure of this type of proofs. Later on, when you talk about convergence of sequences, for example, you're also going to have to prove statements of the form for every something, there exists a something such that blah, blah, blah. They will be a bit more complicated, but the structure is going to be exactly the same. Start by fixing an arbitrary x in this case, find a y, and show that that y works. Usually, the hardest step in the proof is coming up with the y that you need, because that is what requires a lot of thinking and a bit more creativity. Because once you found a y that you know works, it's easy to show that it works. You just have to kind of do all your work backwards. That's, something that we'll worry about more when we're doing more complicated proofs. But for now, all I want you to make sure you understand is the structure of this type of